Hello students, welcome to EPG Pathshala. I am Sunil Kumar from IIT Delhi. So today in this module we are going to discuss about material behavior including load, elasticity, rupture, etc. The topics to be covered in this module are various ways of material classification, crystalline and amorphous materials, good and bad conductors of electricity and thermal energy, mechanical properties, that includes the elastic properties, various types of stress and strain, and the stress-strain relationships, and based on this relationship the classification of materials. So what are the commonly known notions of material classification? So the categorization of materials is a subject of personal choice, as it really depends on the property that is in mind for a specific application or need. Secondly, the commonly used notations for material classification are crystallinity, electrical and thermal conductivity, mechanical strength, elasticity, optical reflectivity, or conductivity. And thirdly, since we are more concerned about the mechanical behavior of various materials which have direct relevance in biology, and hence this will have major focus in this module. Crystallinity. So solids can be classified as crystalline or amorphous depending on the degree of crystallinity, that is the order in the arrangement of constituent atoms or molecules. For pure crystals, the degree can be considered as 1, and for amorphous solids, it is 0. The examples of crystalline solids can be any metal, for example iron or magnesium, potassium nitrate, and so on. An example of amorphous solids can be glass, popularly known glass. So here in this picture, what you have is, in the first one, you have arrangement of atoms in a regular manner such that you have unit cells formed which can be repeated throughout the crystal, throughout the material. So this structure actually is the crystalline structure. In the other picture you have completely random arrangement of atoms or constituent molecules. They do not form a regular structure, they do not have unit cells which can be repeated over the entire material, and hence this is the non-crystalline or amorphous phase of the material. So materials can be found in these two forms, either crystalline or amorphous. The second notion for material classification which is generally used is the electrical conductivity. So materials are classified as electrical conductors, semiconductors, and insulators depending on their capability of transmitting electricity or the flow of charges. Generally all the conductors are metals, or all the metals are conductors. Good conductors have very little resistance against the flow of charges, and hence they are used as electrical wires in your houses. Insulators are the least conducting, and semiconducting materials have intermediate conductivity between the metals and the insulators. So as we said, all metals are conductors, good conductors of electricity. Some examples of semiconducting materials are silicon, germanium, and so on. And some examples from insulating materials can be glass, rubber, plastic, and so on. Similarly, thermal conductivity is another way of material classification. Depending on the thermal conductivity, materials can be classified as conductors, good heat conductors, or bad heat conductors, or thermally insulating materials. So thermal conductivity of a material is the ability to transport heat energy from one region to another within the material. And the carriers for the thermal energy are the electrons and the phonons. Generally, good electrical conductors are good thermal conductors as well, or vice versa. As we said, metals are good electrical conductors and hence they are good thermal conductors as well, meaning they have very good or very high thermal conductivity. Examples of thermal insulators can be wood, plastic, rubber. As an illustration to the transport of heat energy, we take a metal bar, one end of which is hot, meaning high thermal energy. The other end is cold, meaning low thermal energy. The direction of the heat flow is always from the hot end to the cold end. This is in analogy with the electrical conductivity or electrical transport through metal bar. So in that case, you have one end kept at high potential and the other end kept at smaller potential. So the electrical current flows from high potential end to the low potential end. So transport of heat energy is due to either direct flow of the high energy heat carriers or by their collision with low energy heat carriers. So this is the basic principle behind the transport of heat energy or the electrical energy. So it is due to the constituent electrons or phonons. So phonon is a quantum mechanical concept here, or the vibrations of atoms or the constituent molecules of the solids. So these are the main reasons for the transport of electrical or heat energy inside materials. So the metals which have got higher number of electrons, and electrons are good carriers of heat and electrical energy. So that is the reason why metals are good heat and thermal conductors. So mechanical properties. Mechanical properties of materials are intrinsic to each class of material, which determine how they will react to external forces. And what are the properties of the materials that are in mind, which are described as the mechanical properties? They could be the mechanical strength or toughness of any material. Second, how the stress-strain relationship behaves. What is the Poisson ratio? How elastic the material is, meaning in terms of quantification of elasticity, what is the modulus of elasticity? And lastly, fracture strength. So when you want to define a force, stress or strain, then deforming force is the external force that is applied on any solid for bringing about a change in its shape, form or size. That external force is called deforming force. What is stress? So the deforming forces cause an intrinsic stress in the material. Why? Because of the internal forces of the solids. This intrinsic stress is the definition of the stress. What is strain? The amount of change developed in the body, in the material, due to the deforming force is called strain. Mathematically, stress is the ratio between the external force and the area on which it is applied. Similarly, strain is defined as the ratio between the change in the configuration and the original configuration. So let us see how many kinds of stresses and strains you can have in practice. The first type is the normal stress. What is that? So in this one, the external force is applied perpendicular to the surface, meaning the first picture if you look at, here the force F1 is applied perpendicular to the surface, and therefore the stress which gets developed in the material is perpendicular to the surface. In the second one, you have shear or tangential stress, meaning that the applied force and therefore the stress that gets developed in the material is along the tangent to the surface. So stress in the material is developed always opposite to the applied force. That is main thing which you have to keep in mind, that the stress which gets developed inside the material that causes a strain is always opposite to the applied force. Let's think of a block of gelatin having dimensions of 60 mm by 60 mm by 20 mm without any external force. Now you apply a force of 2 Newton tangentially to the upper surface, meaning which has got dimensions of 60 mm by 60 mm. Because of this external force, you have got 5 mm displacement relative to the lower surface, which is fixed. So in this example, can you estimate the shearing stress produced in the block and the direction in which it gets produced, and how much it will vary from the top end to the bottom end when the bottom end is fixed? Can you plot that variation as a function of the depth from the top end to the bottom end? So at the top end, the stress that gets developed, and that is the shear stress, is 555.5 Newton per meter square. So that should be your answer. So what is elasticity? Elasticity is the tendency with which solids oppose the external deformation forces applied on them. Highly elastic materials are those materials which return to their original shape immediately after the external forces are removed. Similarly, highly plastic materials are those materials which cannot return to their original shape and size at all, even after waiting for a long time after you have removed the external deformation forces. In our daily life, elasticity is generally related to how much a body can be stretched by applying an external force. For instance, we say that rubber is more elastic than wax. Why? Because it can be stretched or pressed much more than wax. In practice, no material is perfectly elastic or plastic. According to physics definition, every material is plastic and every material is elastic. The difference lies only in the degree of elasticity. One of the examples of nearly perfect elastic material can be quartz fibers. Similarly, one of the examples of nearly plastic materials can be paraffin wax. Please note here that up to a certain amount of deformation created by the deforming forces, every material can be called elastic, because after the removal of the forces, the original shape and size is recovered. So within the limit of the elasticity, every material is elastic, and beyond that limit, it becomes plastic. So every material is elastic and every material is plastic. It just depends on the limit of elasticity or the degree of the elasticity. So degree of elasticity is basic criteria of defining elasticity or plasticity. Now we ask, what is the kind of stress that you would like to apply to any material before it gets, or so that the material gets broken? What is the limit of the generated deformation below which every material is elastic? So we are talking about two extremes. In one, you apply stresses such that you are in the elastic regime, meaning that you remove the stress and the material returns to its original shape and size. And in the other extreme, you apply an stress such that even after removal of the stress, the material doesn't return to its original shape and size. And eventually, if you just exceed that limit, the material breaks down. So all this can be understood from this strain curves, which are characteristic to every material. What are they? They are the curves between the applied stress or the developed stresses in materials and the strain because of that stress. So in this particular graph here, from A to B, where the strain is proportional to the stress, meaning the response is linear, it is called the elastic region. Point C on this curve, beyond which the behavior of the curves doesn't remain the same, is called the elastic limit. Point D is a point much inside the plastic region that even after force is removed, permanent deformation, the magnitude of which can be seen in the graph as AX, is left in the material. And point E on the stress-strain curve is the point at which the material breaks down. This is called the point of fracture. What is fracture? So with the applied stress, material breaks down after a certain external force applied. Why it happens? At the macroscopic level, great number of deformations take place, which can be, for example, as a result of breaking molecular bonds. For example, here you have this stress-strain curve for a given material, which has been divided into three regions. The linear region, which is called elastic region, where the developed strain is proportional to the applied stress or the stress in the material. And the second region is plastic region, where the developed strain does not linearly depend on the stress. And then you have a point, extreme point, which tells you that if you apply stress any further, the material breaks down. So this point is the point of fracture, in which very little strain is developed by a large stress, and then you have sudden fracture without going to the plastic region. So in the curve you have such materials represented by the blue curve. In the second category you have hard materials, which can be stressed little longer than the brittle materials, and the fracture occurs with a little plastic deformation. In the third category you have ductile materials, which go through the plastic region and then get fractured. So these materials have a very peculiar behavior called necking in the plastic region. And then finally you have plastic materials, which have got very tiny linear elastic region, and most of the time they remain plastic with respect to the applied stresses before they get fractured. As we just learned about the stress-strain curves of materials, in the elastic region, where the strain developed in the material is proportional to the applied stress or the stress generated in the material due to the applied external forces, is basically described in terms of modulus of elasticity, which is mathematically given as the expression E equals stress divided by the strain. So depending on the type of stress and strain, there can be Young's modulus of elasticity, bulk modulus of elasticity, and shear modulus of elasticity. Moduli of elasticity. In the first case, when you have Young's modulus, which is the ability of a material to withstand changes in length when there is lengthwise tension or compression. So mathematically it is given or represented by y, letter y, which is the ratio between the longitudinal stress and the longitudinal strain. In MKS system of units, it has got Newton per meter square unit. So undergoing compression or elongation, the material body should keep its volume unchanged. That is the condition, and therefore a change in cross section will always be accompanied whenever a stress lengthwise or a tension is applied. As an illustration of the Young's modulus, consider a metal bar having cross-sectional area A that is pulled by a force F at each end. So the bar stretches to a new length Ln from the original length L0. The question is, for this particular example, what would be the Young's modulus of elasticity? And that you can immediately see from the diagram. It is going to be the force times the original length divided by the cross-sectional area times the change in the length. Bulk modulus is a measure of the ability of a solid body to withstand changes in its volume when under pressure. So you apply uniform pressure from all around, that is, the external forces are being applied from all the sides of the body, and that results into a change in the volume of the body. So in that case, the bulk modulus is defined as the pressure or the forces per unit area that is required to generate a unit strain, a unit amount of volume strain. Keep in mind that you have all these moduli expressed in Newton per meter square, which is the MKS unit of the modulus. This is illustrated in this slide here. You have a block of certain size which is under forces from all sides, and the forces are balanced, meaning that the body does not move when the forces are applied. Forces are balanced, and therefore they create a uniform pressure on the body. Due to this external pressure P on the solid, which has an initial volume V0, gets compressed to a new volume Vn. So the volumetric strain which gets developed in the body would be simply V0 minus Vn divided by the initial volume V0. In this particular example, the stress that gets developed would be same as the external pressure P, and therefore the bulk modulus will be simply the pressure times the volume of the body divided by the change in volume, Newton per meter square. Lastly, we have shear modulus, which is the ability of any material to resist transverse deformations. So it is the ratio between the shear stress and the shear strain. In this illustration here, you have got a block where the stress is, or the force, external force is applied tangentially to the upper surface. That results to elongation of that surface to an extent of delta L, where L was the original length of that surface. So the shear stress in this example would be simply the force divided by the area of that surface. The strain is delta L divided by the original length L, and therefore the shear modulus will be simply the force times the original length divided by the area of the surface on which the force was applied and divided by the change in the length of that surface from the fixed surface. There is an important quantity that is used to characterize materials, and that is Poisson's ratio. So when a solid is pulled or compressed along its longer dimension, there is a tensile stress or compressional stress that gets developed in it. So Poisson's ratio is defined as the ratio between the strains developed along the lateral direction, that is parallel to the stress, and that perpendicular to it. So if we can use parameter nu to represent the Poisson's ratio, then it is given as minus the lateral strain divided by the axial strain, where the negative sign is because the strain along the shorter dimension, which is the axial dimension, is opposite to the lateral strain, and this is explained in this figure here. For elastic materials, now we would like to understand what is Hooke's law. So in the case of a spring force, we know that for a spring which is fixed at one end, if it gets pulled or compressed or pushed with some force F, then the spring force which gets developed in the spring, first of all, it is opposite to the applied force or the direction of the change of the length of the spring, and secondly, it is proportional to the change in the length of the spring. So for every elastic body, the Hooke's law says that if you compress or pull the body, then there gets developed a spring force Fs, which is opposite to the change in the size of the elastic body times the spring constant or the elastic constant of the body. So it goes same as the spring law or the Hooke's, popularly known as this Hooke's law, but true for every elastic body. Here the spring constant K is a measure of the stiffness or softness of the elastic body on which elastic external forces are applied. So higher the stiffness, higher would be the spring constant. So here are two practice problems which I would like you to try yourselves quickly based on the understanding we have just got from this module. The first problem, a thick uniform rubber rope is considered which has a density of 1.5 gram per centimeter cube, and the Young's modulus for this rope is 5 into 10 to the power 6 Newton per meter square, and the original length of the rope is 8 meter. When this rope is hung from the ceiling of a room, you have to find out what would be the change in the length of the rope due to the weight of the rope itself. And if you do it correctly, the correct answer would be 0.19 meter. In the second practice problem, your leg bones are considered. Typically, they have a cross-sectional area of about 9.50 centimeters square. So if they experience a force of about 855 Newton while you walk, then find the fractional amount or the longitudinal strain your leg bones are compressed by walking. For this problem, you can use the Young's modulus of the bone as y equals 10 to the power 10 Newton per meter square. And if you solve this problem again in the same manner as you did for the first one, then the correct answer would be 9 into 10 to the power minus 5. That is the strain you will develop while you walk in your bone. And you can see that strain is dimensionless parameter, which is a ratio between two lengths in this particular example, or can be between a quantity and the change in that quantity. So strain is always unitless. So to summarize the module, we got familiarized with some of the most basic properties of materials that are used to classify them. Knowledge of these basic properties of solids or materials is very essential, for they dictate the schemes to be followed while designing new materials or tools based on them for various needs and applications. In medical field also, it is very important for the designers of artificial organs or body parts to choose the right material which behaves or has properties according to the needs. We discussed about the elastic and plastic behavior of solids and learned how different materials behave differently under stress. By looking at the stress strain curve of a particular material, one can easily find out if that material is brittle or ductile or plastic. Thank you.